All right, so this is our official final lesson in calculus, and after this, it's going to be all vectors. So take a moment, it's a little bit sad. As we go on, we'll remember all the derivatives we took together. Okay, we're going to return to optimization problems. We're going to take on a couple in this lesson where, one in this lesson where we have like an exponential or a logarithmic thing involved. You'll never have to make an equation. Like I'll never give you a situation and you'll have to come up with the exponential or logarithmic function. That usually requires some sort of scientific research or statistical skills that aren't really part of this course. But somebody figures out, well, this is a good model for this situation, and then we'll use that model to kind of use the calculus and get the max or min for. So I've got one example using the new stuff. I've got one of kind of like just the standard optimization that we could have done last cycle as well. And I'll have some of each type. I think I have one like this and maybe one or two of the regular ones on the next test as well. So optimization continues to be on the next test as well in both forms. Okay, so we've got this situation. The proportion of people that respond to an ad for a new mobile game is given by the function f of t is 0.7 times 1 minus e to the minus 0.2t, where t is the number of days the ads run for. And I just want to start by thinking about what happens if they just continually run this ad forever. So what's going to happen, so I'm just going to draw e to the x, or e to the x. So what's going to happen is this part here, when t gets really, really big, the exponent on e gets really, really negative. So you end up out here on that graph. And so this part of the function, when t is really big, is going to be basically 0, which means we're going to basically have 0.7 times just 1, so 0.7. And so since the function is the proportion of people that respond to the ad, it's showing you kind of the max amount of people that would ever respond. So if they run it forever, we get about 70%, that's the 0.7, respond to the ad. And what we're going to see, that's kind of establishing that our endpoints, because they could run it forever, but that's kind of establishing that it's going to be a bad idea to run it forever, because it does cost them a certain amount per day to run. So eventually they're not getting any new responses, they're not getting any more revenue, and the cost keeps going up and up and up. So that's our hint that the endpoints here aren't necessarily going to be the best idea here. So the ad is available to a population of 10 million people. Each response, so every time somebody responds to the ad, it generates 80 cents for the company. And then we've got some information about the cost. It costs them $35,000 to make the ad, and then they're getting charged $6,000 per day every day that they're running this ad wherever they're running it. And we're going to try and figure out their max profits. So profit equals revenue minus cost, and I didn't really leave any space for you to do this question here, so you're going to want a new piece of paper to do this on. Revenue minus cost. So their revenue is 80 cents times the number of responses, and their cost is 35,000. Yep. Plus 6,000 for every day, so we'll make t the number of days. I think we have already established t is the number of days. Now the number of responses comes from this function that they've given us. They've given us the percent or proportion of people that respond, and it's that proportion of 10 million people. So my number of people that respond is going to be 80 cents times 10 million times that f function, 0.7. And I'll just pass that negative through the second bracket so that I can deal with that. So what I'm going to do now is just clean up that first function a bit. So I'm going to get 0.7 times 0.8 times the 10 million and leave that as a number out front of this bracket here. So that's the, just counting my zeros, that's the 0.7 times 0.8 times 10 million. We still have this bracket with the e function there. And then I'm going to write the minus 6,000 per day minus 35,000. So there's our profit function, simplified as much as we're going to for right now. So we're going to try and find the maximum value here. So we've got to take the derivative of this. So the profit's derivative is going to be, now this is just a number out front. So when you take its derivative, that constant is going to stay out front. The derivative of the inside, well, the derivative of 1 is just 0. So we're just going to get the derivative of e to that function is e to that function times that function's derivative. So we have that. The derivative of minus 6,000t is minus 6,000, and the derivative of the 35,000 is 0. So we're at there. And what I'm going to do, I'm just going to multiply this negative 0.2 times the negative there to make it positive again, and then that times the 5.6 million out front. So there's our derivative, nicely simplified. We need to find any points, any critical values, so where this thing is 0 or where this thing doesn't exist. It's an exponential function. We can plug any amount of days into there, and it'll be fine. So we're just going to solve for where this thing is 0. So we're going to set the other side to 0, bring that 6,000 over, divide by the 1.12 million, and that's going to give us e to the minus 0.2t. Then to get that variable out of the exponent, I'm going to take the log of both sides, and since my base is e, I'm going to take the natural logarithm. And that's going to float the minus 0.2t out of that exponent, leave you with log of e, which is just 1. So the right side simplifies to that. The left side, 6,000 divided by 1.12 million is that. The log of that is negative 5.22, we'll round it off to, and then I'll divide by the minus 0.2, divide by the minus 0.2. And I get 26.1, so we'll round that off to 26 days. So that's our only critical value. For endpoints, if we want to think about endpoints, 0 would be the least amount of days they run this ad. Infinity would be the max. But again, we've talked about how this would be bad since cost keeps going up, but revenue would level off and stay the same, because they get locked at that 70% of the 10 million people have responded. That's all the people that have responded. So the revenue kind of caps out at that, and the cost keeps going up. So that would be bad. So we're going to be thorough, we'll check the profit at 0 to make sure it's worse, and the profit at 26, and we'll see which one's the best. And I bet it's the 26. So I would say that line's probably the easiest for me to plug numbers into right before we took the derivative. So when I plug in 0, the e to the thing becomes 1. So this 5.6 million times 1 minus 1 just goes away. The minus 6,000 goes away because we're timesing that by 0. So we're left with a profit of the negative $35,000. Which makes sense because that was their starting cost and they haven't made any money yet. So as long as we can be profitable at 26 days, that should be the best option. So we get 5.6 million times 1 minus e to the minus 0.2 times 26. And then we have to subtract 6,000 times 26 and subtract the 35,000. I believe that's what we get. So when I plug the 26 into this and multiply by the 5.6 million, I see they get like 5.5 million, almost the full 5.6 million. And then they're losing 156,000 for the cost of running the ad, and then the 35,000 for making the ad. And that balances out to a total profit of we would write a sentence saying that that's the max profit for the company. So the company should run the ad for 26 days and they'll make $5.4 million at the end of the day, which is, I'm guessing, a pretty good payday for them. Okay, I'm going to jump over and look at number 2, which is a problem I believe that you did with Mr. Marshall then. So we're going to create an open top box to be constructed with equal size squares cut out of each corner. The starting piece of cardboard is 100 by 100, and we're going to decide how big of a cut to make to maximize the volume. So I'm just going to find some space for me to draw this out. So I believe, yeah, Mr. Marshall usually does this in advanced functions. So you have the piece of cardboard. Now that we know calculus, we can get to an exact answer, hopefully a lot faster than you were able to before. And we're going to cut an equal size square out of each corner and then fold up the tabs and make a box. So we're going to call the amount we cut x, and then we think about these sides would be 100 minus 2x, these pieces of the box. Same with that and that, because we're cutting 2 x's out of 100. And then the height of the box would just be x when you fold up those tabs. So something like that. And we're going to have to do the derivative of that, so I might as well expand. That's probably the easiest way to do that. 4 zeros, so I'm just going to do this bracket times the, whoa, what did I do? Microphone axis. I'm going to multiply the 2 first brackets, and then I'll just multiply the x in as I go. So I get that times x, so minus 200 minus another 200x. So I believe that's going to be minus 400x, and when I multiply by the other x, I'm going to get an x squared. And then my last term, negative 2 times negative 2 is positive 4, and x cubed when I multiply all those x's together. So there is our volume function. The derivative of that is going to be, and I'm going to write them in the right order, so I'm going to start this way, 12x squared minus 800x, and then plus 10,000, something like that. And we just need to find that thing. It's a parabola. It exists everywhere. We just need to find where it's 0. So let's see what we get. What do I want to do? Take a 4 out. Probably the biggest that'll go out is a 4. Yeah. I'll factor out a 4 to make it smaller to deal with. Yes, I put that in the calculator. I didn't want to make a mistake on video. That would be embarrassing. Okay. So probably factors I'm not going to bother trying. I'm just going to jump to the quadratic formula now with that smaller quadratic in there. And yeah, since that square root worked out to a nice even number, it would have factored if we would have tried, but we didn't. So I'm going to get two answers here. I'm going to get x equals 300 divided by 6, which is 50. And I'm going to get x equals 100 divided by 6, which is 16.67. 6 repeating value. So those are my two potential answers there. So what I can do now is I could, since we have two critical values here, we want to establish which one of them is actually a max. We could plug them into the original with the endpoints and figure out which one's actually the max. That's probably the way I'll go. Or you could do a factor table and show that, well, this one will be the max. So you can show that in a factor table as well, a factor table of the derivative. So when I think about endpoints here, though, the smallest cut you could make from that corner is x. And since we're taking x out of each side, the biggest cut you could make is that 50, because that's going to cut away the full box, because I'd cut 50 here and 50 there, and then there's no more cardboard left to fold. So that's how I'm going to establish my endpoints. And we'll see that that critical value is actually one of the endpoints. So my volume function, which is, I'll just rewrite it up here so I can see it. When I plug in 0, that x at the end is 0, and I'm multiplying, so the volume is going to be 0. When I plug in 50, the first two brackets are both 0, so I'll multiply and get 0. And when I plug in 16.67, I should get a wonderful answer. And I'm going to actually calculate each bracket down to a number, because now I see the length, width, and height of the resulting box. And I get my large volume, my maximum volume. I'll just round it off to 1. That many centimeters cubed. So we could say, therefore, they should cut 16.67 out of each corner. The resulting dimensions of the box are 66.67 times 66.67 by 16.7, and the maximum volume is the 74,096.3. So that could answer any possible question I might ask about this box in that sentence I just said out loud. So that's it. That's my calculus examples. I believe the practice here all involves exponentials, so I've given you the functions you need to work with. I don't even think they're like the first one where you have to use that to build a new. I think it's just giving you, yeah, that is the profit, that is the revenue, determine, yeah, so that is the revenue, and this is the percent of people. So again, yeah, it's given you the function you need to work with. You don't need to build it. You're just doing the maximization steps.